Okay, well, I'm gonna go with the 17 people that we have in the class at this point. Oh, 18. Okay, keeps going up. Okay, hopefully the rest of the people will catch up. Okay, we're gonna cover 16.8 today. Stokes theorem, or Stokes's theorem. Stokes's. Okay. So let's write out what Stokes' theorem is. Okay, let S be an oriented piecewise smooth surface that is bounded by simple closed that's an M closed piecewise smooth boundary curve with positive orientation. Okay. So what does that look like? Say that we have this surface. Okay. And oops. Okay, so we have this surface, and the idea that it's opening upward. Okay, it's positive orientation. Okay, and that C is going counterclockwise. C is the boundary curve. Think of it as like the shoreline for a lake. Okay, so C is the boundary curve. Okay, and we have positive orientation for the surface, which means that all of the normal unit vectors coming off of this force field are pointing up. Okay, so all the normal unit vectors off of this surface are pointing upward. Okay, so if this is true, okay, then we let F be a vector field whose components have continuous partial derivatives on an open region in R3 that contains S. Okay, so if these conditions are met, which they are going to be for all the stuff that we're going to do today, okay, if these conditions are met, okay, then Stokes' theorem says that we can change interchangeably the line integral that's going around the surface with the double integral of the curl, okay, of f dot ds. So this goes forwards and backwards. Okay, that's what Stokes' theorem is saying here, is that we can exchange a line integral for a surface integral, or vice versa. We can exchange the surface integral for a line integral. Okay, so they're under these conditions, they're interchangeable. Okay. Okay, so basically we have a line integral to a surface integral okay, or vice versa. Okay, line integral to surface integral or surface integral back to line integral. So we can utilize the tools that we have for line integrals, okay, to get the surface integral, or we can utilize the tools that we have for surface integrals, okay, to get a line integral that wouldn't be as easily gotten. Okay, it's basically a form of the fundamental theorem of calculus. We're taking, okay, an integration and we're reducing it to, we're saying we have, you know, a double integral and we're reducing it to a single integral or vice versa. Okay, so let's do an example of this. Okay, we want to evaluate, okay, the line integral f dot dr, where our vector field, okay, our force field is x, y, z equals negative y squared I plus xj plus z squared k. Okay, so that's our force field. Okay, and C is the curve of the intersection of the plane y plus z equals 2 and the cylinder x squared plus y squared equals 1. Okay, so we want to evaluate this, blah, 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 using Stokes' theorem. Okay. Okay. And we can say that C has positive orientation. Okay, so we want to evaluate this line integral using Stokes' theorem. Okay, so let's do that. Okay, this is a three-dimensional, okay, force field, and we're having to do a line integral on that. So We could parametrize that, but the intersection of the plane, again, it would get tricky to try to find an R value for C. Okay, so Stokes' theorem is helpful when it's hard to find, you know, exactly what is the parametrization of curve C. In this case, it's the intersection of a cylinder and a plane. So if we were to intersect a cylinder with a plane, okay, like what would this look like? Okay, and we would get, okay, kind of this ellipse type of shape. Okay, we're intersecting, you know, if it was flat, then yeah, it would be a circle, but we're cutting into this at some sort of angle, because it's y plus z equals 2 is the plane that we're looking at, or more importantly, z equals 2 minus y. Okay, so that's the plane that's slicing this cylinder, and it's creating some form of an ellipse. Okay, and we're saying that this is now C. Okay, C is this line integral that goes around C. Okay, but you know, it includes you know, Z here. Okay, so it's going around this slice into the cylinder. Okay, and it has positive orientation. Okay, so let's say that the line integral is going to be equal to the double integral over the surface of this thing, okay, of the curl. Okay, so the line integral is really over the surface, that slice, okay, of the curl of f dot ds. Okay, so let's change the line integral into a surface integral, okay, and see if that helps us. Let's find the curl of f. Curl of f, remember, is just a gradient crossed with f. So we've got I, j, k, and we've got d dx, d dy, d dz. Okay, and then up here, what was our f? It was negative y squared. Okay, and then it was x, and then it was z squared. Okay, so let's take the curl of this thing. Okay, this is going to be d dy z squared minus d dz x I. Okay, minus, okay, d dx z squared, d dx z squared minus d dz negative y squared. Okay, j plus, this is going to be d dx x minus d dy of negative y squared k. Okay, well, we can easily see that the partial with respect to y of z squared, that goes to 0. Okay, partial of on z with respect to x, that also goes to 0. Partial with respect to x of z squared, that goes to 0. And partial with respect to z of y squared, that goes to 0. Okay, so all of those goes to 0. Okay, partial of with respect to x of x, that's 1. And then minus a minus here, partial with respect to y of negative y squared. That's negative 2y. So that's a negative of negative 2y. Okay, k. So the only thing that survives there is the k term. Okay. So and this is 1 plus 2y, k. Okay, so we have this s, okay, and then the curl, okay, the curl of f dotted with ds. Okay, so this is 1 plus 2y dotted with ds. Okay, this is k. Well, let's not worry about that just yet. Let's go back to the curl of f dot ds. Okay. Okay. So we've changed this into a line integral into a double integral, okay, over s. Okay, and if we go back to last session, okay, we saw that this was true. If we take our surface integral, okay, of f dot ds, which is called our flux, by the way. Okay, if we take our flux of f dot dx and by parametrizing, okay, x equals x, y equals y, and z equals g of x, y, then we can rewrite it as a double integral over its projection using this formula here, okay, where pi plus qj plus rk. So we're going to do that. And instead of just having f, we're going to let that be the curl of f. Okay. So the curl of f is going to take on our f. Well, what was the curl of f? The curl of f is this guy here. So we're just going to let that be our new f. Okay, so the curl of f is equal to, okay, pi plus qj plus rk, right? So what's p, q, and r in this case? Well, p has to be 0, right? Because this is 1 plus 2y k. Okay, 1 plus 2y k. So p is 0, q is 0, and r is 1 plus 2y. Okay, so this thing is going to be d over negative p dg dx minus q dg dy plus r. Okay. Okay, and that's going to be over dA, the area of the projection in D. Okay. Okay, so right, so that's where P, Q, and R come from the curl of F, not F itself. Okay. Where P, Q, and R come from the curl of F and not F itself. Okay. Okay, so we're going to rewrite this, okay, as D, okay, over, well, we need to know what G is. What's G in this case? G, okay, G is the equation of the surface here, okay, And what is the equation of that surface? Well, it is a plane. It's an isolated plane, but it is just a plane. And I can rewrite z equaling 2 minus y. Okay, that's that plane that's slicing my cylinder. The cylinder just puts boundaries on the surface. Okay, it just cuts it into a smaller surface, but the surface behavior is this plane z equals 2 minus y. And so this I can write as g of xy is equal to 2 minus y. So if I plug this in, if I take the partial of g with respect to x, then this becomes 0. Okay, but the partial of g with respect to y, okay, becomes -1. Okay, so plugging all of this in, what are we going to get? Well, we're going to plug this in, we're going to get d. Negative p, well, what was p? I'll circle these things that we want here. Okay, what was p? Well, p was 0. What was dg dx? It was 0. Okay, so that whole term goes to 0. Minus q, what was q? Q was 0. Okay, times -1. Okay, which is dg dy. And then plus r. Well, what was r? R was 1 plus 2y, and then this is dA. dA being the projection of that. Okay, so we have d. This goes away, that goes away. And we have 1 plus 2y dA. Okay, now this is in rectangular coordinates. The problem is that the projection of this thing onto the xy plane is a circle. Okay, so again, if we were to slice this thing, like so. Okay, the projection on D is a circle, and so we want to use circular coordinates, which we call polar coordinates, right? So we want to change this guy into polar coordinates. So how could I change this guy into polar coordinates? Well, this is going to be 1 plus 2r sine theta, right, times r dr d theta. We're changing from rectangular to polar, right? And so what's r going to go from? Well, r is going to go from 0 to 1 because it's the unit circle is d. And then what's theta going to go from? Well, it's going to be 1 rotation of 0 to 2 pi. Now, let's continue with this, and then I want to kind of pinpoint something that we haven't that might be confusing. Okay, so let's go and let's just distribute r. Okay, this is r plus 2r squared sine theta dr d theta. Okay, integrate from 0 to 1 and 0 to 2 pi. Okay, so now let's integrate with respect to r squared over 2 plus 2/3 r cubed sine theta evaluated from 0 to 1. Since both of these contain an r being multiplied, it just simplifies to 1/2 plus 2/3 sine theta. Now we want to integrate this from 0 to 2 pi d theta. Okay, so this is going to be 1/2 theta minus 2/3 cosine theta, right? Evaluated from 0 to 2 pi. Okay, so plugging in 2 pi, we get 1/2 times 2 pi minus 2/3 times the cosine of 2 pi. Well, cosine of 2 pi is just 1. So I'm just going to put a 1 there. Okay, minus, okay, 1/2 of 0, okay, minus 2/3 times the cosine of 0. But what is the cosine of 0? Well, that's just 1 again. Okay, so this becomes pi minus 2/3. This is going to get me minus 0. And this is going to get me plus 2/3. That goes away, and we're left with just pi. Okay, so what was pi? Pi was our line integral, okay, around okay, so it was this line integral here, okay, around our slanted ellipse, okay, and that ended up being, okay, a length of pi, okay. Okay, now one thing to keep in mind is that parametrizing is not the same as converting. Okay, converting coordinates. Okay, parametrizing something is not the same as converting coordinates. Okay, if I parametrize something, say I have, something in terms of x, y, and z, f of x, y, and z, right? And say that, I don't want to think about this. We have, say, xi plus yj plus zk, right? And then we could say that z is equal to, say, 1 plus x squared, okay? So we have this, these parameters, x, y, and z is equal to 1 plus x squared, right? So we would set up these parameters, okay, and then we would do either a double integral or a triple integral on these parameters, okay? So keep in mind that if you're changing parameters, even if you're saying that x is equal to, say, sine of, x is cosine theta, y is sine theta, and z equals 1 plus I don't know, sine theta, however you're doing this, okay, this is not the same as converting converting coordinates. Converting coordinates for this guy, you'd have to have, if you were to do like an r, let's plug in an r here, okay, you'd have to do an r d theta if you converted from, say this was, x, x plus y plus z, right, dA, okay, of d. If you were to convert this to polar, you'd have to have an r d theta. Okay, but if you parametrize a force field, you don't. You would just go directly to, okay, the r's and thetas. I hope that makes a little bit of sense there. Parametrizing is not the same as converting coordinates. Okay, converting coordinates, you're integrating over a rectangular area in rectangular coordinates, and then you're converting to polar. Okay, parametrizing, you're given coordinates, but you're putting it into a parametric form, and you're just evaluating on those 1 or 2 parameters. Okay, so you've already done the converting before you even do the integration, if that makes sense. You've already done the converting, because a good example of this, okay, is if we have our line integral, right? What did we say before this was? Well, this was equal to, okay, f r of t dot r prime of t dt. Now look at this. We already have our conversion factor in this. Okay, that r prime of t there. Okay, so we have that conversion factor in there. We again, if we do instead of a line integral, we parameterize a surface integral. Okay, f dot ds. Well, how would we? Oops, I don't want an equal sign there. Okay, as f dot ds. Okay, we're going to parameterize this thing. Okay, so how did we parameterize that? Which is f of uv, right? F of u, r of uv. Okay, f of r of uv, and then it was the magnitude of ru cross rv. Okay, right, and then this was, would be dv du. Okay, so notice that again, this thing, this ru cross rv, that's behaving like this r prime of t. Okay, so we parameterized, and this is our kind of fudge factor, our integration factor, mind you, that we're getting. So you don't have to convert and then convert. You've already converted before you do the integration. The conversion came before the integration. Okay, not after. If we set up the integral and then we have to convert, then we have to include the integration factor there of conversion. So I don't know if that made any sense, but again, just one thing that I noticed in going over some of these problems might have been a little confusing. Okay, it was like, well, when do you put in your integration factor and when do you not? Well, these are the integration factors. Okay, so if you're changing it to an r and theta, okay, then this will be your r dr d theta basically. Okay, so yeah. Okay, let's do another one of these Stokes theorem problems. Okay, number 2, use Stokes theorem, okay, to compute the integral of s of the curl of f dot ds. Okay, so we want to use Stokes theorem. So generally when we're talking about Stokes theorem, or we talk about the next thing, which is divergence theorem, they're wanting you to go one direction to the other direction. Okay, so they're going to give you information either for the curl of f, or they're going to and the surface, or they're going to give you information about the line integral and want you to go and get the curl. So in this case, we want to find this curl of f dot ds, but we want to use, okay, using the line integral. Okay, now this problem can actually be done both ways. Okay, I didn't choose a hard problem. You can do it both ways. You could find it using the surface integral, or you could do it using the line integral. Now, one of the ways is going to be easier than the other, and so that's why we have Stokes theorem, because sometimes it's easier to do the surface integral, but if the surface is really weird and wonky, and it's a closed surface, it's a closed boundary, then we want to use the line integral. Okay, because that one's going to be easier. We would go with whichever one's easier. Now, in this specific problem, they want you to use the line integral to find the surface integral. But again, this could be done either way. Either way, doesn't matter on this one because it's a fairly benign problem. It's fairly easy. Okay, so find this using this. Again, we could go forwards and backwards with this. That's the power of this theorem. Okay, so that one is the same as the other. Okay, where f is equal to xzi plus yzj plus xyk. Okay, and S, the surface, is the part of the sphere x squared plus y squared plus z squared equals 4 that lies inside the cylinder x squared plus y squared equals 1 and above the xy plane. Okay. Okay, so what is this looking like? Well, if we have the sphere, okay, and we want this thing to lie above the xy plane, what are we really taking? We're really taking the hemisphere, the top hemisphere. Does that make sense? If it's above the xy plane, the surface is above the xy plane, then we just take the hemisphere, top hemisphere. Okay, so let's just look at the top hemisphere for this thing. Okay. And now it says taking this top hemisphere. Now, what's the radius of this sphere? Well, the radius is 2, right? So we would have a radius of 2. Okay, radius of 2. Now, inside the sphere is a cylinder. I don't like this. Let's just use marks to mark off our. Okay. To use those marks. Okay, so inside the sphere is a cylinder, okay, of radius 1. Okay, and so the top here looks like this. Okay, and this surface here is really what we're looking at. We're looking at this surface at the very top that is on the sphere of radius 2, but within that cylinder of radius 1. Okay. Okay, so what does C look like? Right? Because we want to use the line integral, okay, of this thing. Well, what does C look like? Well, C is part of a circle. Okay, it's a circle of radius 1. Okay, but it's at a certain z value. Okay, at a certain height. So let me change colors here. So what is C? Let me make that thicker. Okay, C is going to be this guy here. I'm putting it in green. Okay, this is C. Okay, C is just my boundary around that surface. Okay, it's kind of like a little, it's not, I wouldn't say, it's a convex, like, what do I want to say? Like a lens almost. Like think of the cornea of your eye. Okay, we're going around the cornea of your eye, of your eyeball. Okay. It's a convex surface. Okay, like the cornea of your eye, your eyeballs. Okay, so this is C. Okay, C, right there. Okay, makes sense. Okay, so how are we going to get that equation for C? Right? What is C going to be? Okay, we have F. We have F. F is given to us in IJK. Okay, but I'd really like to use this to get the curl. Okay, and I want to parameterize that the function as well. So let's do that. In order to find C, C is the intersection Okay, so C is the intersection of x squared plus y squared plus z squared equals 4 and okay, x squared plus y squared equals 1. So what is that intersection? What is the intersection there? Well, if x squared plus y squared equals 1, then can't I just replace x squared plus y squared with 1? Well, sure. So 1 plus z squared equals 4. Z squared equals 3. So z would equal plus or minus 3. Or sorry, radical 3. Plus or minus radical 3. But where are we? Aren't we above the xy plane? So we can eliminate that minus. And so z is equal to okay, radical 3. That's where we are. We're up here, okay, at radical 3. We're there at radical 3. Okay, so what is C? What's the surface C? Well, C is x squared plus y squared equals 1, comma, z equals radical 3. That's this plane. If I were to slice this plane through, okay, through this cornea. I don't really want to talk about slicing eyeballs. That's kind of disgusting. But if you were to slice off the cornea of your eyeball, then where's that knife edge? Yeah, things are getting way too disgusting here. Okay. Let's try to change the analogy. I don't know. It's a good analogy. At least it'll be memorable. Okay, so we're going to slice this thing at the plane z equals radical 3. Okay, so these are my constraints on what C is. C is within the circle. Okay, it's the boundary of the circle, but it's at z equals radical 3, that plane. Okay. Okay, so what would R of t be for C? R of t. We want to parameterize this thing, right? R of t equals C. Okay, so, well, how could I rewrite x and y in terms of a parameter t? X and y in terms of a parameter t. Well, isn't this just the unit circle? Right? Isn't that just a unit circle? So couldn't I just say, oh, this is cosine theta I plus sine theta j plus, and then what's k going to be here? Well, isn't k just going to be radical 3? Yeah. Okay, so remember, what's the goal here? The goal here is that we want f dot dr to be equal to, okay, the integral, okay, of f of r of t dotted with r prime of t dt. That's the goal here. Okay, so if we can parameterize this, or in our case, this is r of theta, and so we're going to just replace these t's with thetas in this case. R prime of theta d theta. Okay, now, did I have to convert to from rectangular to polar? No. Why did I not have to convert from rectangular to polar? Because it's a parametric. We already parameterized this thing. It's already done. Okay, it's in terms of theta, but it's a vector. It's a vector parameterization of that that curve. Okay, this specific curve in 3 space. Okay, so what is f in this case? Okay, so what was f? F was equal to, if we go way back to our original, f was equal to xzi plus yzj plus xyk. Okay, so what is x in this case? X is cosine theta, y is sine theta, and z is radical 3, right? So this is going to be equal to, okay, f of, we'll say r of theta, is going to be equal to x, which is cosine theta, times radical 3. So that's radical 3 cosine theta I, okay, plus, okay, radical 3 cosine theta, or sorry, sine theta j plus, okay, xy is going to be cosine theta sine theta k. Okay, so now what do we want to do with this thing? Well, we want to dot product this with r prime of t, or r prime of theta, right? Isn't that the idea here? We go back to this step here. Okay, we wanted to dot that with r. Well, what's r prime of theta? Well, let's figure out what r prime of theta is. So take this guy up here, okay, and take the derivative of him. Okay, well, what's the derivative of cosine? Well, it's negative sine of theta. I got 2 j's there. This is I. Okay, plus what's the derivative of sine? Well, that's cosine. And what's the derivative of a constant? Well, that's 0. Now what am I going to do? Now I'm going to dot product the two, right? I'm going to dot product the two. So this thing becomes dotted, okay, the top function, f of r of theta, becomes dotted with the bottom function. So we're just going to multiply those together and then add the components. So this becomes negative radical 3 sine theta cosine theta. This becomes plus radical 3 sine theta cosine theta. Oh, that's nice. Those cancel. And then plus 0 times cosine theta sine theta. And that goes to 0. So the whole thing goes to 0. Okay, d theta. Okay, but what's our parameter on theta? What is theta allowed to be? Okay, if we parameterize this in r of theta is equal to the unit circle here. Okay, then what is theta allowed to be? Well, it's allowed to go one cycle around the unit circle. So c in this case is 0 to 2 pi, okay? Probably should have written that up here where theta is 0 to 2 pi, okay? Okay, so 0 to 2 pi of 0 d theta, okay, that becomes 0 minus 0, which is 0. So the whole thing goes to 0. Okay, so that's the curl of f. Dot ds. Okay, so that's what the curl of that is. Okay, the surface integral of the curl. Okay, so that's 16.8. Okay, let's move into 16.9. Okay, 16.9 is called the divergence theorem. Okay, the divergence theorem. Okay, I kind of like the thicker pen there. Let's see. Okay, so we're going to define, okay, the positive orientation of a solid. Okay, positive orientation of a solid as outward. And negative as inward. Okay, so what does this mean? Okay, say that we have a solid. Okay, I'm just going to draw a box. Okay, say we have a solid. We're going to call this solid E. Okay, name is E. E the solid. And if the forces are going outward, okay, then on E, then that's positive orientation. If the forces are, so if E is expanding, okay, then we say that's positive orientation. If E is compressing, okay, so expanding is positive. Okay, compressing is negative. Okay, let's compare this to surfaces and lines. Okay, if I had a closed line C, what was positive orientation in this case? Positive was counterclockwise. Negative was clockwise. Okay. What about for a surface? Okay, what about for a surface? Okay, so okay, for a surface, what was positive and what was negative? Well, positive was upward and negative was downward. Okay, so positive was upward and negative was downward. And that's the orientation of the normal vectors. Okay, if the normal vectors shot upward, then it was positive, and if it was downward. Now, for a solid, we're moving from one-dimensional to two dimensionals now into three dimensionals. Okay, so we're going to be dealing with three dimensionals. Solids. Okay, so we talked about a line. Okay, line and in quotation marks, line. It's not really a line, it's a curve. Okay, so, whoops. Okay, so we have this curve. Okay, and then the surface. And then we have this solid, right? This solid. Okay, so we went from one dimension to two dimensions, and now we're going to step it up a notch to three dimensions. Okay. So let's define the divergence theorem. Okay, the divergence theorem. The divergence theorem. Okay, let E be a simple solid region and let S be the boundary surface of E with positive or outward orientation, period. Let F be a vector field whose component functions have continuous partial derivatives on an open region that contains E. Okay, then the following is true. Then the surface integral of f dot dx, okay, this surface integral f dot ds has a special name. Okay, this surface integral f dot ds has a special name. It's called the flux. Okay, so that is called the flux. Okay, is equal to, the flux is then equal to a triple integral over E, okay, which is our solid, of the divergence of F dV. So very similar to Stokes' theorem, right? Recall that, what was Stokes' theorem? Stokes' theorem was taking a line integral and equating it to a surface integral, right? E there. Okay, so taking a line integral to a surface integral, okay, this was the curl of f dot ds over s, right? So this was Stokes' theorem. So the divergence theorem is now taking it up a notch. And it's saying, look, we can, in Stokes' theorem, we converted line integrals to surface integrals, or vice versa. We converted surface integrals back to line integrals. we could go forwards and backwards at will. Okay. And but what about for higher dimensions, right? Let's move this up a dimension. Now let's take the surface integral, and what are we going to convert that to? Well, this triple integral over E, over the solid E, okay, of the volume with the divergence, this is called a hypervolume. It's a volume in 4 dimensions, okay, which is hard to visualize because we don't live in 4 dimensions. But it's called the hypervolume. We're changing the flux into the hypervolume. Okay. Okay, so let's do an example of this. Okay. Find the flux. Okay, aka surface integral. Okay, of the vector field. F equals Zi plus Yj plus Xk over E. What's E? Okay, over E in this case. E over E, where E is the ball. Okay, x squared plus y squared plus z squared equals 1. Okay, now again, what's the difference between a ball and a sphere? A ball includes all of the mass inside. The sphere is just the outside. Okay. Okay, so this is a ball. Okay, over this. Okay, so how do we want to find this? This is f of s dot ds. That's the flux. Okay, and then we're going to change this to a triple integral over just the sphere. Okay. Okay, just the surface. I'm sorry. We're changing this from the surface integral of the sphere into the ball. Okay. The 3-dimensional solid. Okay. And we're doing that using the divergence of f dot dv dot the volume here. So E is this ball here. Okay. So what's the divergence of f going to be? Well, what's the divergence of f? Remember, that was just the gradient of f. It was the gradient of f. Okay. So what's the gradient of f? Okay. Gradient of f, that's going to be ddx of, sorry, ddx of z, okay, well, it's really not it's the gradient dotted with f. Okay, so the gradient dotted with f is what the divergence is. Okay, it's ddx of z plus ddy of y plus ddz of x. Okay, so it's the gradient. Okay, del. Okay, so del dot f. Okay, whatever. So this is 0 plus 1 plus 0, which is 1. Okay, so that's 1. Okay, so we're going to have a triple integral of 1, okay, dot dv, okay, dot dv over e. Now what are we going to want to do here? This is in rectangular coordinates at the moment. Okay, 3 space, x, y, and z. Okay, so but we're wanting to do a triple integral over this ball. And so what are we going to have to do? Well, we're going to have to convert, okay, this that is currently in rectangular coordinates. Why? How do we know it was in rectangular coordinates? Because we just took our partials with respect to x, y, and z. That's how we know it's in rectangular coordinates. We didn't parametrize f. Okay, we did not parametrize f. So we are going to have to convert this to spherical coordinates. Okay, so let's convert this to spherical coordinates. This is 1 times p squared sine of phi times dp d phi d theta. Okay, and so that's a 1. Okay. And so what are our limits of integration? Well, what does p go from? Well, it goes from 0 to 1. That's the radius of the ball. Okay. And then what's phi go from? It's 0 to pi. And what's theta go from? Well, it's 0 to 2 pi. Okay, so let's integrate this and see what we get. This is with respect to p first. So this is p cubed over 3 sine of phi, right? Evaluated from 0 to 1. So that's just going to be 1/3 sine of phi. Okay, we want to integrate this now with respect to phi from 0 to pi. So that's going to be negative 1/3 cosine phi from 0 to pi. Okay, plugging in pi, I get negative 1. So this is negative 1/3 times negative 1 minus, excuse me, minus 1/3 times the cosine of 0, which is 1. Right? Cosine of 0 is 1. This is minus, this is minus a negative 1/3. It's minus a negative 1/3 times cosine of 0, which is 1. So this becomes negative negative, which is a positive 1/3, plus a positive 1/3, which is a positive 2/3. We're going to integrate that from 0 to 2 pi of 2/3 d theta. This becomes 2/3 theta. Integrated or evaluated from 0 to 2 pi. So this just becomes 4 pi over 3. Okay, 4 pi over 3. Which is a similar result to what we got last time. So let me just refresh your memory here. Okay, it is a different function for f that we're evaluating, but we ended up with the same result as something that we did last time. So let's go back to 16.7. Okay. So not that one. Okay, and here, okay, we did roughly a very similar problem. Okay, so it says number 2 on 16.7, compute the surface integral of s, okay, of x squared ds, where s is the unit sphere, x squared plus y squared plus z squared equals 1. Okay, so then we did parametrize this, okay, and we got x squared ds equals f of r of uv magnitude of RU cross RV dA. And then we went through the parameterization of this, okay? And we just want to find out what's the magnitude of this thing, okay? The magnitude of this, okay, ended up being sine of, okay, sine of phi, okay? And so we plugged it all back in, okay, sine of phi, okay, of this thing here, sine phi cosine theta squared, okay, and then we plugged it, did all the integration, okay, on phi, and we came out with 4 pi over 3. So we did have to, you know, get a cross product here. It seemed to be a lot more work, and it was. It is a lot more work. Okay, finding the divergence is a lot easier than finding the cross product, and so we came out with a similar result. Okay, but it took us a lot more work. I just wanted to show you that the divergence theorem makes short work or shorter work of a similar problem. Okay, so it did not have that tool in our tool belt last time. Okay, for 16.7, because we didn't have Stokes theorem or divergence theorem as a tool in our tool belt. Okay, let's do the last example for today. Okay, here we're going to go backwards. Okay, we're going to want to find, okay, a surface integral using the divergence. Okay, so find the surface integral using the divergence. Okay, so using a triple integral. Okay, so number 2 here. Evaluate the flux. Okay, F dot ds. Evaluate the flux. Okay, where f of x, y, z is our force field, our vector field. Okay, x, y, I plus y squared plus e to the x z squared j plus sine of x, y, k. Okay, and S is the surface of the region bounded by the parabolic cylinder z equals 1 minus x squared, and the planes z equals 0, y equals 0, and y plus z equals 2. Okay, so y plus z equals 2. Okay, so let's see what this looks like. Okay, so we have a, let me draw my coordinates here, my grid. Okay, so we have in 3 space, we have z, a cylinder, z equals x minus 1, right? So I'm going to get some numbers here out here. The 1, okay, 1, 2, 1, 2, 1, 2, and I'm even going to go this way. 1, 2, 1, 2. Okay, we good? Okay. So we want to know, what is z equal 1 minus x squared? Well, that's, notice that that has no y value. So y can be anything I want it to be. But the x's and the z's are restricted to a parabola, and it's an upside down parabola. Okay, if z is 0, then x is plus or minus 1. If x is 0, then z is 1. Okay, so this is x, y, and z. Okay, so what this looks like is it's a parabola that goes like this. Okay, now this extends along the z axis forever. Okay, it's a cylinder. Okay, does that make sense? It's a parabolic cylinder. It extends. Okay. Okay, but this is bounded. This is bounded above by the xy plane. Okay, it's bounded z, because z is 0. It's bounded above by z equaling 0, which is the xy plane. It's also bounded by the zx plane, because y is 0. It's the xy plane. This is the zx plane. Okay, so stop here, but it's also bounded by this plane, x plus z equals 2. Well, what does that plane look like? Well, if I let y be 0, then I would get 0, 0. If I let x and y be 0, I get 0, 0, 2. Well, where is it 0, 0, 2? Well, it's right here. This is 0, 0, 2. If I let y be, if I let z be 0, then I get 0, 2, 0. Okay, let z be 0. I get 0, 2, 0. And so we get a plane that's kind of slicing through. Maybe I'll do a different color here. We get a plane that's kind of slicing through like so. Okay, and so what does this look like? Well, I'm going to get rid of a couple of these things here. I'm going to erase this guy. Don't want him anymore. He's gone. I don't want this guy. He's gone. And I don't want this guy either. He's gone. Okay. What does this look like? Well, this looks like this. Okay. It's more slanted. Oops. Okay. And then, nope, I don't like that. Get rid of these lines here. Okay. So it goes through that. Let me get rid of this one because it can't go below it either. Bring this guy in. Okay. And the idea here, okay, is that this should look like this. Okay, parallel to the x-axis. This should come in like so. And then where these two meet, that is slanted. Does that make sense? It's slanted along that plane. Okay, that's the plane y y plus z equals 2. Okay, so this is the solid that I'm looking at. Okay. So what's this? This is the solid that I'm looking at. Bring that back. There we go. Nice. Okay, and then I could even connect this as well if I wanted to. Okay, but you should get the idea there. Okay. Okay, so let's find the flux of this thing. Okay, the flux of f dot ds over s over this surface, right? The surface is going to be equal to the triple integral over the solid of the divergence of f with respect to the volume now. We're going to find the volume. Okay, so what's the divergence of f? The divergence of f. Okay, well, what was f to begin with? F was xyi, right? So xyi plus y squared plus e to the x z squared j plus sine xy k. Okay, so if we take the divergence of this, we're just going to take the partials with respect to x, y, and z, and then add them up. Well, what's the partial with respect to x of xy? Well, that's just y. Okay. What's the partial with respect to divergence of f, right? Okay, what's the partial with respect to y of this thing? Well, e to the x z squared, that doesn't contain a y, so that just goes to 0. Goes to 0. Okay, and this becomes 2y. What about sine of xy? Well, that doesn't contain a z, right? So this is d dx, this is d dy, this is d dz, right? This doesn't contain a z, so that goes to 0. So we're just left with y plus 2y, which is 3y. Okay, that's the divergence. So we have a triple integral over 3y of dv, okay, of our volume here. Okay, so how can we figure out what our volume is? Well, we have to figure out, well, what's our restrictions on x, y, and z? Okay, x, y, and z. Okay. Okay, so let's look at z first. What is z being? How is z being restricted? Z is being restricted from 0 to 1 minus x squared. That's how z is being restricted, right? Okay, what about y? How is y being restricted? Well, y is being restricted from 0 to what? This is y here. So y is being restricted from the plane y equals 0, which is this thing here, to the plane y equals 2 minus 2 minus z. So this is to 2 minus z. Okay, the plane 2 minus z. Does that make sense? Because it was y plus z equals 2, so 2 minus z is equal to y equals 2 minus z, right? So that's the plane 2 minus z, okay, with respect to y. Okay, and then what about x? What's x being restricted from? Well, x is really just being restricted from -1 to 1, because it's that cylinder. So that's -1 to 1. Okay. So this is going to help me write my limits of integration in correct order. Okay. So notice that I have y in terms of z, I have z in terms of x, and then I have x in just in terms of numbers. So I know that the x is going to have to go last. Okay, so I'm going to get 3y. And then dx is going to have to go last. Now I want to know, do I want to put z in terms of x, y in terms of z? What order is this going to go? Well, if I have x last, then I have to have something in terms of just x's, and that's z, right? So this would be dz would be next to last, so that would go 0 to 1 minus x squared, because I want to end up with something in terms of just x when I integrate that. And then, so what's that going to leave me doing first? Well, doing first is going to be my y, because that's in terms of my next variable, z. So y is going to be 0 to 2 minus z. So now we can integrate. Okay. So this is going to become 3/2 y squared evaluated from 0 to 2 minus z. Okay, plug in the 2 minus z, we get 3/2 times 2 minus z squared. Okay, we could do a u sub on this. Okay, u is equal to 2 minus z, so du would equal negative dz, right? Okay, so you do your u sub on that. It would just become 3/2 1/3 times 2 minus z cubed. I'm substituting back in, but I'd have an extra negative here. So this would be negative. Okay, and then I would evaluate that, okay, from 0 to okay, 0 to 1 minus x squared. Okay. Okay, the 3's are obviously going to cancel out. Okay, I'm going to plug in 1 minus x squared in for z. Okay, so this is going to be negative 1/2 times 2 minus 1 minus x squared cubed. Okay. Okay, so I integrated and then I integrated again, basically. This is 0 to 1 minus x squared. We've already done 2 of the integrations. dz. Okay, so now I just want to clean this up, distribute the negative 1. This becomes x squared plus 1. Okay, cubed, negative 1/2 on the outside. Okay, plug that in. That becomes, and then it's minus. If I plug in the 0, that doesn't go away. If I plug in the 0, this becomes minus a minus 1/2 times 2 minus 0 cubed. Okay. Okay, so this is going to be plus 1/2 times 2 cubed. 2 cubed is 8. So this is minus 1/2 times x squared plus 1 cubed plus 4. Okay, now we're going to integrate this all with respect to x. Okay, now for me, I don't really want to deal with a u sub on this. It just is going to be kind of a nightmare to do a u sub. If we do x squared plus 1 equals u, then we don't have an x. We don't have an extra x to throw in there. So what I'm going to do is I'm just actually going to multiply all of this out. Okay, x squared plus 1, that's actually pretty easy to find. Just use Pascal's triangle for that. This is minus 1/2 times. This is going to be x to the 6th. That's x squared to the 3rd. Okay, plus 3 x to the 4th times 1, which is just x to the 4th, plus 3 x squared. Okay, plus 1. Okay, plus 1. 1 times 1 times 1 is 1. 1 cubed. Okay, and then plus 4. Okay, and so what this is going to allow me to do is integrate term by term, which is kind of nice. This is I can distribute the 1/2 if I want. I don't have to, but I might do that to clean up the last term here. Okay, so this is going to be negative 1/2 x to the 6th minus 3/2 x to the 4th minus 3/2 x squared minus 1/2 plus 4. Okay, so and this thing is just going to become 7/2. So now let's integrate term by term. Okay, so this thing is going to become negative 1/14 x to the 7th minus 3/10 x to the 5th minus 1/2 x to the 3rd plus 7/2 x from negative 1 to 1. Okay, so let's plug in our 1 first. That becomes negative 1/14 minus 3/10 minus 1/2 plus 7/2. Okay, minus, okay, plug in the negative. All of these are odd powers. Okay, even the last one is an odd power. So all the signs are going to change. So this is going to become 1/14 plus 3/10 plus 1/2 minus 7/2. But if I distribute the negative, all the signs stay the same. So we did a negative of a negative. So this is negative 1/14 plus negative 1/14, that's negative 2/14, which is negative 1/7. This is negative 3/10 minus 3/10, that's negative 6/10, which is negative 3/5. This is negative 1/2 plus 7/2, that's 6/2, that's going to be positive 3. So this is a positive 3. This is another positive 3. So that's positive 6. Okay, so positive 6. So this is going to give me, multiply both top and bottom by 5 here, multiply both top and bottom by 7 here. And we get negative 5 and negative 21, which is negative 26 over 35 plus 6. Okay, so 6 minus, so 35 minus 26 is 9. So this is 5 and 9/35. Okay, which if you wanted to make it an improper fraction, this would be 184 over 35. Okay, and that's the answer to that one. Okay, so that's the flux. Okay, over that surface. Over that surface, which is the same as the triple integral of the solid of the divergence. Okay, and that's it. We've covered all of the material in Calc 3. Okay, so now it's just review for the exam and review for the final. Okay, review for exam 4, and then review for the final. And the finally, we're not really having a review because the final is going to be sent to you as a take-home final. Okay, I'll post it 24 hours before it's due, so you'll have a whole 24 hours to work on it. Okay, and then it'll be due on that Tuesday, finals day. Okay, so yeah, there was a question about the homework grade in Canvas. The homework grade in Canvas is a is just an estimate right now. It's a low estimate of what you would have in the course if you didn't do anything else from here on out. Okay, for the homework, just the homework, not the exams. Okay, so the homework grade just doesn't include these last few assignments. And so it's a low boundary. And the reason I did that was there are some people in here, a couple people in here that are in danger of failing. And I wanted to make sure that they had the opportunity to see what their grade would be going into the last two exams without, you know, if they chose to blow off my assignments from here on out, you know, what would be the lowest that they could possibly be getting, you know, at this point in time. And so, yeah, so, you know, with the options of, you know, an excused withdrawal or pass, no pass at this point, I just wanted to send that message out to those people. Okay, if you're not in danger of failing, then, you know, your homework grade will go up the more assignments that you complete at this point. Okay, including the assignments for 16.8 and 16.9, which we covered today. Okay, so I will post the review. The review will be posted in 2 hours. So exam 4 review will be posted in two hours from now at 12 o'clock. Let me think if there's anything else that I want to announce before we all go. Exam review. Nope. Yeah, let me look at the exam review real quick. Okay, yeah, it includes just 10 questions. Yeah, okay, and we'll begin that on Tuesday. Okay, so the exam review just contains 10 questions of what I should feel that you should know for similar to questions that are on the exam. They're not identical. Okay, they might not even be all inclusive, but it's just a smattering of topics that I think that you should know from chapter 16. Okay. Okay, we'll go over that on Tuesday. Okay. Okay. With that, if there's no other questions, I will see you guys later. You're welcome. You too.